Hello, everyone, and welcome back to another Planetarium show. My name is Jessica. I'm the director of the Planetarium, and with me tonight are two probably familiar faces if you've been here before. They're students who work in the Planetarium, and I will let them introduce themselves, starting off with who's going to be our host tonight.
Hi, I'm Lindsay. I'm a physics graduate student at UMD.
I'm Eli. I'm a physics undergraduate student at UMD.
So, tonight we have a super fun show for you looking at how physics is used by animals and insects and other living creatures other than humans. It's fascinating, and Lindsay has just some awesome stuff to share with us. So before I turn it over to her, as usual, if you have any questions throughout the show tonight, leave them down in the comments. Eli and I will keep an eye on those, and we'll let Lindsay know as questions come up. We'll also have time at the end to answer questions as well. So with that, Lindsay, it is all yours, and I'm just realizing I don't think I gave you permission to share screen. Okay, you should have that now. It is all yours.
Okay. All right, so welcome to Phurry Physics. I always love trying to find physics in, everyday life. And so we are going to look at it in the animal kingdom today. First, we're going to look at color, how animals get color. First, we kind of need to know what color is. So white light is actually made up of all the different colors of the rainbow. And the light coming from the sun is white light. Now, each of these colors, red, orange, yellow, green, blue, indigo, violet, they all have different wavelengths and frequencies. So when they get to the glass, they slow down, but they slow down different amounts because they all have their different wavelengths and frequencies. And so that's why the white light gets spread out in the glass. So with pigment is one way that animals can get their color. We'll look more closely at this on the next slide. So you have sunlight, again, it's white light made up of all the colors of the rainbow. The leaf absorbs all of the colors except for green, which gets reflected back up to your eye, which is why the leaf looks green. So here's a little more specific diagram. So we have a cardinal over here. It has red feathers, and it has red feathers because it has red pigments. So we have the sun over here, light coming from the sun is made up of all the different colors. And so they start to spread out as they go through this top layer, keratin cortex. And then the pigment granules, they absorb all of the colors but red. So no matter what angle you look at this bird with, or yeah, the pigment is always going to be the same. So here's some more animals that are colored by pigment. Ladybug, polar bears, frogs. Okay, so another way that animals can get their color is through structure. So just like how we have this white light coming in and then hitting the glass prism and then slowing down, and each of the colors kind of getting spread out, that can happen actually with animals. So this is called iridescence. So this bird has some nice iridescence right here on the chest. So the feathers are a little bit more complicated. Again, we have our white light coming in from the sun. We have that top layer that is a keratin cortex. Then we have a layer of melanin nodules, and then we have another keratin layer, and then another layer of the melanin nodules. So in this case, let's follow the color purple. So we have purple coming in from the sunlight, and the keratin cortex, reflects that purple up here at a particular angle. So just like with this prism, how the colors are all at different angles when they go into the glass prism, that's the same thing that is happening here. So if you are at this angle, you will see that purple light. But if you are at a different angle, let's go over here, green, then you will only see green light, because the angle of the purple light and the blue light is such that they won't go into your eyes. So the angle that you are looking at the bird from determines the colors that you will see. So this is a snake that has some iridescent scales. You can also get color from the structure, but in this case, it's non-iridescent. So with this bird's feathers, they're going to be the same color all the time, but instead of having a pigment causing that, it's actually the structure of the feathers. So we have our sunlight coming in, we have a keratin cortex, a spongy layer, and then black melanin layer on bottom. So again, this spongy layer causes blue light to reflect back out at us and into your eye to make the bird look blue all the time. Here's a couple more blue things. We have a butterfly here and another bird. And we can also relate it to our eyes. So we have this structure that is making this bird blue. And so actually in nature, there is no pigment that can make something blue. Something can only be blue if the skin is like this and it reflects blue back to your eye. So blue is kind of rare in nature because, again, the only way that it can happen is if the butterfly or the bird have the right kind of structures in their wings or feathers. So with our eyes, blue eyes do not have any blue pigment in them. The only reason that they're blue is just the structure of the eye reflects and refracts light so that when people are looking at you, the blue light, they see the blue light coming out of your eyes. And for brown, those actually do have pigment in them. So now we're going to talk about a different type of light, UV light. So in addition to all of the colors of the rainbow coming from the sunlight, we also get ultraviolet light from the sun. So it's a high energy wave, and then it gets absorbed by a material, and then it re-emits visible light. So this first part of the ultraviolet light, you can't actually see it, but after it is absorbed and then re-emitted in visible light, then you can see it. Okay, so this is called fluorescence, and coral is one of the animals that actually do fluorescence. Scientists are not entirely sure why animals fluoresce. In this case, for the coral, it might be kind of a protector from the sun. So, you know, part of their skin kind of absorbs all of that UV light coming in from the sun, which helps them be protected from that UV light. Another animal that fluoresces is a scorpion. So it's possible that the scorpion is also fluorescing because it needs some protection from the sun. So that is providing some sunscreen for it. But another idea actually has to do with the scorpion knowing whether or not it is well hidden from predators. So of course, the animal kingdom, it's important to evade the predators that are coming after you. And so with a scorpion, if it's halfway in a hole, scientists think that maybe this half of the scorpion that is out in the sunlight and fluorescing tells the scorpion that it's not all in the hole and it needs to be more in the hole. Bioluminescence. So this happens when we have light going in and then a particular molecule in the cell causing the light. There's lots of different reasons that animals can fluoresce. So they can startle other fishes, counter illumination, use it as a misdirection, distract with your glowing body parts, burglar alarm, sacrificial tag, or a warning. Can also be used to lure prey and stun or confuse prey and illuminate prey. And sometimes the bioluminescence is used for mate attraction. Okay, now we are going to talk about, this is probably my favorite part of this. I love color, but this is probably my favorite part of this. Magnetoreception. This is the ability of animals to be able to detect Earth's magnetic field. It's super cool.
The glimmer of light leads you to the shoreline. Suddenly, a wave pulls you in. At first, you use the direction of the waves to guide you. But once you're in the open sea, with powerful currents bombarding you, and very little light, how can you be sure of where you are and where you're going? For a hatchling sea turtle, the answer is magnetoreception. That's the ability to sense magnetic fields. We know many animals use this sixth sense for navigation. What we don't know is exactly how magnetoreception works. Here's what we do know. Earth itself is like a giant magnet. The motion from its liquid outer core generates a magnetic field. Certain animals can sense this field and use it as a compass to tell them if they're heading in the right direction, and a map to give them signposts along the way.
There's two competing theories for how magnetoreception works. One is a chemical sensor, the other is a mechanical sensor.
The first theory is that animals have tiny magnetite particles in their bodies that act as magnetic receptors. Magnetite is the most magnetic natural metal on Earth. It's been found in many animals that exhibit magnetoreception.
And it's thought that it's the only potential sensor that would be sensitive enough to capture these incredibly tiny variations in magnetic field strength that would allow the animal to not just know whether they're going north or south along the magnetic field line, but know the precise beach that they need to get to.
The other theory is that animals possess a protein in their eyes called cryptochrome, which allows them to see magnetic fields. Cryptochrome has been found in the eyes of several migratory birds, but we haven't proven either theory for a few reasons.
With magnetoreception, you don't know where to look. Magnetic fields pass invisibly through the entire body, so researchers don't know exactly where these magnetite particles or cryptochromes would be attached to particular cells. I mean, so mistakes are made all the time.
And so far, cryptochrome experiments have only yielded positive results in the presence of magnetic fields much stronger than Earth's.
The frontier is now not so much at the animal behavior level, but actually getting inside the brains of these animals and trying to find these sensing cells and connecting them to the neural circuitry. It's not so much a question of which animals have this sense, but which don't. So researchers have said, well, why not humans? Maybe we had this sense at one point deep in our evolutionary past and lost it, but maybe there's a vestige left. Researchers in California and Japan have gone after this holy grail one more time with a very specialized experiment, one that relies on double blinding and magnetic shielding, and they're seeing glimmers, maybe even more than glimmers, of this magnetic sense in humans. It's starting to be reproducible, and they're really excited about it.
So some of the animals that use magnetoreception, in addition to the ones in the video, we have a naked, or sorry, not a naked mole rat, but a Zambian mole rat. We have a bumblebee, and we have a type of pigeon. This is my other favorite animal video. So foxes also, it seems, have this magnetoreception, and it helps them catch their prey. And so when you're watching this video, also look at some of the other physics that the foxes use, like projectile motion.
Winter in the Yellowstone National Park. The snow here is regularly more than 2 meters deep. A red fox can survive here all winter, but only if it can find enough food. Their ability to pinpoint rodents beneath the thick layer of snow has always been attributed to their exceptional hearing. And that is part of the process. Foxes can move each ear independently, rotating them up to 150 degrees. More than a dozen separate muscles finely tune the position of the ear canal so the fox can identify a sound and locate it more accurately. But in 2010, scientists uncovered something astonishing. It's long been known that to reach the prey beneath the snow, or even in thick grass, foxes use a technique called a mouse pounce. What this recent survey found was that the overall hit rate was just 18%. But when the fox faced in a northeasterly direction, the hit rate rose to a staggering 73%. Unbelievably, the foxes seem to be aligning their pounces to the Earth's magnetic field, which tilts downward in the northern hemisphere. It's thought that the fox can detect this magnetism. As the fox creeps forward, it listens for the sound of a mouse, searching for that sweet spot where the angle of the sound hitting its ears matches the slope of the Earth's magnetic field. When it finds that spot, the fox knows that the prey is a fixed distance away, and it can calculate exactly how far to jump to land right on top of it. Scientists think that the secret behind this talent might be a protein in the fox's eye called cryptochrome, which is sensitive to the Earth's natural magnetism. What's more, they speculate that this might actually allow them to see the magnetic field as a patch in their vision. If the scientists are correct, the red fox will be the first animal known to use the Earth's magnetic field to hunt.
Okay, so now we are going to go on to some animals that are using the stars to navigate instead of the magnetic field. So this is a wild-caught Indian bunting. And there was actually an experiment done with these birds in 1967 in a planetarium. They wanted to find out kind of how how the birds figure out that they're going south. So if it's star patterns or if they just know which direction, internally what direction south is. So they set up an experiment in a planetarium with some constellations projected up on the ceiling. And no matter what direction those constellation patterns were that the birds follow, they would go in that direction. So instead of just having an internal feeling about which way south is, they use the star patterns to navigate. Luckily, the star patterns they use are always in the south, so they can always get to the south. Okay, the dung beetle. So it uses actually the Milky Way to help it navigate. So the Milky Way is the fuzzy band of stars and clouds and dust up in the night sky. And you have the dung beetle rolling this ball. And it wants to make sure that it doesn't end up where it started, because then that would be pointless. So it follows the light of the Milky Way in the sky as it goes, so that it knows that it is going in a straight line and it will not end up back where it started. Okay, animals that can walk on water. Okay, so water tension makes water as a fluid kind of unique. So the way that the molecules in the water droplet fit together causes kind of a round surface. So when you drop a drop of water on a surface, it doesn't flatten out like you might think it would. Instead, it just balls up, and because of the water tension, just stays as this little ball of water. So this spider is using water tension to stay above the water and walk on water. So all of these legs are using water or the surface tension to walk. So the spider, though, has to be careful that it is not applying too much force. If it applies too much force, it will break through the surface tension of the water, and then it won't be walking on water anymore. Okay, next, animals and sound. Okay, so crickets, they have like one side of their wing has a file on it, and the other side of their wing has a scraper. And they rub those two things together to make their cricket sound. And so these create vibrations that also create sound. So we have the wings, and they are physically rubbing up against each other. That creates a sound. But then the physically rubbing against each other causes the wings to kind of vibrate, and then that causes a noise also. That causes sound. So lots of different ways that the crickets are making sounds. The club-winged manakin also makes sound with its wings. It kind of has the same setup as the cricket, where you have one side that's kind of like a razor, and then the other side where you rub the razor against it. And these clubwind mannequins can beat their feathers or their wings together 107 times per second. So that is just like so fast. So they use this sound sometimes to attract mates. Okay, and echolocation. You may have heard of this one. Oopsie. So we have some sound waves coming out and then bouncing back off an object. So then the bat knows that the object is there.
Think of a cat silently stalking a bird, or a rattlesnake ready to ambush a mouse without rustling a leaf on the forest floor. An owl can swoop down on a mouse without making a sound. Silence is the cloaking device predators use to capture a meal. Now consider bats, whales, dolphins, porpoises, and a few other animals that use their voices to find prey. Through echolocation, these animals emit sounds of different frequencies and loudness that bounce off the objects around them. The echoes are then captured by the ears, and the brain figures out how to recognize food and navigate the surroundings from those signals. Some bats emit sound blasts that are so loud they could deafen human hearing. Only we cannot hear their ultrasonic voices. The world would sound quite different if we could. Like whales and dolphins that use echolocation in water, bats use their voices to see the world through air, and very effectively. A katydid rests motionless on a leaf, one of thousands of leaves on a tree. The insect doesn't make a peep. The night is black. A leaf-nosed bat flying nearby blasts the tree with sonar at ultrasound frequency, then listens. It sees the katydid with the echo created from sonar and swoops in for the kill. No human-made sonar equipment can detect objects with such finesse. In fact, the most sophisticated submarine sonar system, large as a house, cannot see the world nearly as well as a bat. Leaf-nosed bats are at the pinnacle of echolocating animals. Their fleshy noses are like musical instruments that amplify and focus the sounds made with their larynx. In fact, their noses change shape to produce different sounds for scanning different objects in the surroundings. Their ears are also capable of shape-shifting to capture the sensory information they need at any moment, so they can fly in the dark without hitting tree limbs or power lines, communicate with each other, and pick an insect meal from dense vegetation with surgical precision.
I actually got to hear bats echolocating once. I was at Bryce Canyon National Park and I was out at night looking at the stars, and I was the only person in like, I don't know, a few hundred feet. So it was just me, and I could, yeah, hear the little clicks of the bats as they were echolocating.
Gotta remember to unmute myself on the other thing. That's very cool. It looks like we just got a question.
That just popped up for me too.
So, how much does varying moonlight affect color visibility at night? Does moonlight variance affect night predators?
Yeah, absolutely. And you don't actually know how much light the moon provides until you are in a place with no light pollution and no moon. Like I was, again, in Bryce Canyon National Park, and I'm pulling up to an intersection and I look both ways. It was pointless because I couldn't see anything because the moon was not out. So yeah, the moon definitely affects, or the amount of moonlight that is there definitely affects animals. But also this is why we're trying to reduce light pollution, because that is kind of getting mixed in with the moonlight and also affecting those animals that are affected by the moonlight.
Yeah, I mean, there's probably a very good reason they often call the like big full moons like hunter's moons. 'Cause they definitely make it easier for the predators to find their prey. And I know that there have been studies in how light pollution is affecting the animals that use things like starlight to navigate star patterns, because if those star patterns aren't visible, then they're lost. I think isn't there also instances of like the dung beetle like heading towards cities instead of where they actually want to go because they're seeing that bright light instead of the Milky Way light.
Yeah.
So yeah, lots of different things going on, and one of the many reasons why, like Lindsay said, we definitely advocate for preserving dark skies.
Not just to see, a beautiful night sky. That's just a bonus, but also to help all of these animals that rely on that moonlight.
Yeah.
Yeah. A lot of like nighttime predators do see less success when they're hunting because like whatever they're preying on can see them. So it causes a lot of problems for
Yeah,
nighttime.
that's true. There's that too. And I mean, I think a lot of people get worried when hearing things like minimize light pollution because they think we just want to turn all lights off everywhere.
Just
And
use them.
that's not the case at all. There are ways to have lights, but use them efficiently to help us see, but to minimize the light pollution effect that they have. In fact, the color of lights that we use is huge. For some reason, people are really liking using these like really bright blue lights, and those are actually horrible for our night vision. Our night vision is much better used with warmer colors like red lights. So even that simple switch, it would make things easier on us and would also make like passing that car with the obnoxious bright blue lights not happen. And one of the reasons it's so obnoxious is that disrupts your night vision. And that's why you go blind all of a sudden. Because yeah, you're being overwhelmed by all of this light that your eyes aren't used to because it's in night mode, and there's a lot, and this is probably a whole other show topic that we can do.
That's why if any of you have ever been in the planetarium, when we bring the lights on after the star show, we do the red light because if we get the blue light, it would hurt.
And trust us, we've done it to ourselves.
Grab the wrong knob.
There is a group out there that is trying to get the lights in Duluth changed from cool lights to warmer lights.
Yeah. Or even simply like having a shield over the top so the light points down rather than up. Because you don't need up light anyway, that's wasted light.
Right.
But yeah, we got a little off topic from animals, although we are animals, I guess. We can include us. But no, I always love that show. I think I agree with you. The foxes are my favorite. I love that video.
Amazing physicists.
Seriously. I mean, yeah, they're the user ears. They're like, I mean, I know college students who can't do projectile motion, let alone, a fox. It's crazy.
I am one of those college students.
You can do projectile motion. Don't even.
I don't remember it.
All right. I am not seeing any other questions at the moment. If anyone does have any others, great time to leave them down in the comments. And while we give that a minute to see if anything else comes in, let me tell you what's coming up over the next week. So on Saturday is going to be our latest edition of our exploration series, and we're going to take a close-up look at our closest star, the Sun. Then next week, and I say this every month, next week is June, somehow. So we will do our usual beginning of the month shows. So we'll have next Wednesday, What's Up, June edition, and next Saturday, the June constellation story time. Of course, we are still offering our private virtual shows. If you're interested in doing that, we do both field trips and general public private shows. Like we've done quite a few birthday parties, online virtual birthday parties, which have been a lot of fun. And if you missed it in the kind of pre-show slideshow that's up before we go, before you see our beautiful faces, we finally have our new t-shirt designs out. And there is a link to where you can see those in the video description. We're super excited for these. We've got some amazing ones. And, huge shout out to Big Frog and Duluth for partnering with us and helping us provide this online store and doing all the printing and shipping and stuff for us. Because I've learned doing shipping ourselves is a lot more work than I thought it would be. All right. Well, I'm not seeing any other questions come through. So, Lindsay, thank you for another awesome show. Yes. And I know that we're excited to turn that into an actual, full dome experience once we get back in the planetarium. And I hope to have some news on that soon. Wink, wink. I guess I'll just go ahead and say it. We are hoping to open up the summer for private shows. And fingers crossed we can get the planetarium back open to the general public for our maybe regular schedule. We'll see what things are by the end of the summer. But there's a good reason we're waiting till the end of the summer. We've got a lot of great updates and things going on that we want to be completed before we reopen for the general show public and stuff. But you can find news about that will go out as soon as it is official. So hopefully any day now we will get the green light for that. All right. Well, thank you everyone so much for hanging out with us this evening. We hope you enjoyed the show. Be sure to check us out on other nights. We stream regularly on Wednesdays and Saturdays at 7 p.m. Central, and we will continue to do so until we are back fully reopened. And maybe we'll keep some things. We'll see. We've gotten a few requests from people to keep going even after we reopen, but we'll see how it goes. All right. Have a wonderful rest of your evening, everyone, and we will see you next time. Bye.